So Unit 3, Lesson 4 is logarithmic functions. And we're exploring the inverse of an exponential function. In this example, we're going to consider the exponential function y equals 2 to the x. Looking at it algebraically, if we take the inverse, we're switching the x and y, and we get this. Now, what are we asked to do here? Attempt to determine the inverse of this, and we get this. Now, typically we solve for y, so we go y equals, or what do we do to get this off the exponent and written just as a variable? A little bit of difficulty. Basically, we don't know how to solve for y. So we are actually unable to write the inverse in terms of y. We can rearrange the x and y, but that's as far as we get. Okay, exploring the inverse graphically. Now we know to reflect y equals 2 to the x in the line x equals y. So here is y equals 2 to the x, and the inverse would be this here, reflection in the x equals y line. We can take some x values and figure out the y, plot, and then we just switch these around. Negative 3 1/8 becomes 1/8 negative 3, and so on. We can plot that. Okay. Alright, let's take a look at the next part below. So in the note here it says that y equals 2 to the x is the exponential function with a base of 2. The inverse is this. It's also a function, as you see from the graph that I looked at above. Vertical line tests only goes through once, but at the moment we're unable to write the equation in terms of y. But to do this, we introduce a new function called the logarithmic function. And it's actually the inverse of an exponential function. So on your calculator, you'll notice that you have the button 10 to the x, and that's also paired with log. 1 here, well, you need to press second function to go from one to the other, or shift to go from one to the other on your calculator. It's just indicating that these are inverses of each other. Now the inverse of the exponential function with base 2 is the log function with base 2. This here is now what y equals if we use logs. So how this is read is we would say y equals log of x to the base 2. Note that this graph, if we plot it on our calculator, is the same as the one above, this one here, when we took the reflection of y equals 2 to the x. So these are one and the same thing. Now, in general, we write y equals log x to the base b rather than x equals b to the y if we're going to express the inverse of this. Again, we want to express it, solve for y. Now, basically what logging does is that when you have this equation here, logging both sides allows you to bring the x to the front. I'll show you basically, and it may show below when we move down, but what we're doing to this is we're logging this. I believe it will show us how to do that below, so I won't go into it at the moment. Let's read on here. The log function with base b has this equation. X in any log function here, what we're logging has to be greater than 0. Well, no, actually, just for this particular equation, I believe x has to be greater than 0. Where x all values greater than 0 can be members of the real number set. B has to be greater than 0 always, whatever the base number is. And B cannot be equal to 1. That's one restriction for the base. Okay. Now, inside of the log function, in this case, the inside of the log function, in this case x, this guy here, is called the argument of the logarithm. And the argument here can never be negative. So in fact, yes, it looks like, sorry, this value x can never be negative. B is the base, and y is just the value. So I just want to say something about converting between this version of the inverse and this version of the inverse. To go from one to the other, to go to in the forward direction, converting to a log, you're solving for the exponent. So you're solving for y, you log the value of x, and this remains as the base number, which is put down as a subscript below the log here. So we can solve for the exponent and write log x to the base 2. Okay, so I'll let you read over this example 1. It's asking you to write and label which one is y equals log x base 2. Complete the table below to fill in the domain and range for both functions. Just have a look at the graph and fill them in yourself on your own book, and then refer to this to see if you've got it right. Example 2. Tables below show the coordinates of points on the graphs, on both these graphs. One's the inverse of the other. Okay. So you can see some points of x, points of y, and we had these points in our tables at the beginning of this lesson. Notice that 0.38 on the graph of this, x is 3, y is 8, is indicating this. Okay, and the 0.83, which is really the inverse, if we use the inverse equation, putting 8 for x and 3 for y, it's writing it as 3 equals log of 8 base 2. A. What statement can be made from the point -2, 1/4 on the graph of this? We can simply substitute in values of x and y. X is -2, y is 1/4. So substituting in, we can see that this is true. Concurrently, what statement can be made from the point 16,4 on the graph of y equals log x base 2? Y is 4, x is 16, so we get 4 equals log 16 base 2. So bear with us here as we go through these examples. I know logs are new terminology, but we'll explain here what it's all about. Completing the table below, showing statements in exponential and log form. In log form, we have log of 8 base 2 is equal to 3, or 8 equals 2 to the 3. Log 4 base 2 equals 2, or 4 equals 2 to the 2. Log 2 base 2 happens to equal 1. Another way to look at that is 2 equals 2 to the 1 in exponential form. If you have log 1 base 2, it equals 0. Another way to write that is that 1 equals 2 to the 0 in exponential form. So 1 being the inverse of the other. Carrying on here, if we use log of 8 base 2 equals to -3, we can write that as 1/8 equals 2 to the, and I believe that's negative. I'm going to have to cube root. I think it's -2 over sorry, so that's negative 3, sorry. Negative 3. Log of a quarter base 2 is negative 2, or 1/4 in the exponential form equals 2 to the negative 2. And then log a half base 2 is negative 1, so a half equals 2 to the negative 1. Notice the trend here in going from 8 to 4 to 2 to 1. It's going, values are going from 3 to 2 to 1 to 0. We can actually write this 4 as a, well, actually start with 8. We can actually write the 8 as 2 to the 3. So log 2 to the 3 to the base 2 is 3. This 4 is really 2 to the 2. This 2 is 2 to the 1, and so on. So the exponent is actually giving the value of these. If we log 2 to the base 2 to the 3, the value is 3. If we log 2 to the base 2 and the exponent's 2, the value is 2. If we log 2 to the base 2 and the exponent's 1, and so on, we get value 1. So this is giving us the exponent as the answer. Okay. If we move over here, this is really 2 to the negative 3, so negative 3 becomes the answer. This is 2 to the negative 2, so negative 2 becomes the answer, and so on. So the general trend is that if we have log x, and this is base 2, 3, whatever it happens to be, let's put it as base 3. Actually, let's give it base 2 for now, make it simple on ourselves. And this value here happens to be, I don't know, let's call it to the a. Actually, let's scrub that for a minute. If we get log 2 to the 2 and this value is a, then our answer is a. And just extrapolating that, if we've got log of 5 to the base 5, and this is a, the answer is also a. We'll also find that something like log to the log of b base b is equal to 1 always. If these two numbers are the same, log b to base b will always equal 1. It's sort of what's happening down here. Okay. Example 3. Use patterns developed from class example 2 to write the exponential statement for 10 to the 3 equaling 1,000. Now if we do this in log form, this gets logged, and this becomes the base number. Sorry, 10 is the base, and we're solving for 3. So we log the 1,000. 10 is the base, we solve for the exponent, and here we are here. Guess what? If it's 10 to the 5, the answer, which is in this case 10,000, if we log both sides, or log this, the log of 10,000, actually that should be 4 here, my apologies, that's going to equal 4. If there was 5 zeros, this would equal 5. If there was 6 zeros, this would equal 6, and so on. So let's solve using same patterns. Let's rewrite this in exponential form. So we're reversing. This is actually going to be our exponent right here. This will be our base, so it's going to be 5 to the 4, and that's going to equal 625. Now, I have an easy way to remember how to go from log to exponent, and if you can remember somehow exponent to log, that'd be good. It's called the drop, swing, and bump method. In going from this version to basically this version, we drop down the number, so 1,000. We swing the 10 over, bumping the 3 up. It's called the drop, and swing and bump. Drop, swing, bump. You can change from log to exponential. So in this version here we got log 625 was equal to 4. If we drop down the 625, swing over the 5 and bump the 4 up, we get that. Okay, I'm going to pause this and do a second part because this is going to be a long lesson by the looks of it. So we'll pick that up in part 2.